Okay, our last kind of subtopic that we're going to be discussing is open and closed systems and how they relate to conservation of mass. Okay, so you're going to have a worksheet, a digital worksheet that you're going to need to open up, and you'll have that in a separate window as my lecture. So you'll be running them both at the same time. You'll have the two windows open. And as we go through and discuss open and closed systems, I'm going to fill in blanks in your notes, and I would like you to fill in the blanks on your worksheet and then submit that to me as your notes, and I'll give you a grade for your notes. So, a system is considered to be a group of two or more parts that work together to carry out a function, like all the parts of a pen that work together to help that pen function to write. We might even talk about a person as a system and all the different parts of the person that work together in order to help this individual function. The one that we're mostly going to focus on right now, because we're talking about conservation of mass, is experiments. And we might even consider a test tube or an Erlenmeyer flask or a beaker our system and talk about the reactants and the products and if they are able to go in and come out of that system. So we have two main types of systems. We have an open system in which matter and energy can freely cross the boundary of a system. So, a great example of this would be a pot of water on a stove. Okay. If we don't have a lid on the pot, this system is considered to be an open system. And heat energy can be lost from the pot to the air or transferred from the pot to the air um, across the system boundary. Out of the pot. In addition to that, if some of the water molecules that make up the liquid in the pot gain enough heat energy and they bump into each other hard enough, they can escape that pot as a gas. And so, in that case, we can see matter is also free to cross the boundary of the system and leave the pot and go into the air. Okay, a closed system is a little bit different. Okay, a closed system is one in which energy can cross the boundary of the system, but matter cannot. Okay, so this is showing us a pressure cooker full of water. So a pressure cooker is sealed and you plug it in and it heats up. So this is an example of a closed system because there's this lid on there. And in a closed system, the outside of this pot can still get hot. And so we do have some heat transfer. So that's where the energy can still be transferred. But because we have this sealed lid, none of the water molecules can leave as a gas. Okay, they're trapped within that system. So we'll see no loss of mass within the pot because it's a closed system. Or I should say, not loss of mass, but transfer to the air. Okay, so for this unit, though, we're only going to think about open and closed systems in terms of the flow of matter. We're not going to so much focus on energy because we want to discuss the law of conservation of mass, which tells us that matter can never be created or destroyed. So if you look at this model of a chemical reaction, and this is telling us that this is iron. So this is composed of a group of iron atoms and a group of sulfur atoms, and they're chemically reacting to form a new compound that we would call iron sulfide. So this is showing us conservation of mass, because if we look at the left-hand side of the equation, this pictorial equation of a chemical reaction, where the reactants are, we would be able to count that there's 3, 6, 9 atoms of iron on the left. And then if we look on the right side of the equation, looks like I have a typo here. It should say right side and right side down here as well. On the right side of the equation, again, if we look at those orange atoms, 1, 2, 3, 4, 5, 6, 7, 8, 9 atoms of iron coming out of the reaction. We have 3, 6, 9 atoms of sulfur going in. And 1, 2, 3, we're counting the red atoms here, 4, 5, 6, 7, 8, 9 sulfur atoms coming out of the reaction. So this visual reaction is showing us conservation of mass because we have 9 atoms of iron going in, 9 coming out, 9 atoms of sulfur going in, 9 atoms coming out. So these glass tanks below each represent a system. And if we look at them very closely, we should see that this one is open. So this is an open system, and this one is a closed system. Okay, so the reason that we know this is basically the container on the left, which is this one right here, has no lid, so matter and energy can leave and enter the system. Okay, the container on the right, okay, has a lid, so matter cannot enter or leave the system. Okay, and if you need me to go a little bit slower with that and kind of put it up here for you so you can write it down. The container on the left has no lid, so matter and energy can leave and enter the system. So water could evaporate, an insect could fly in there, and so we have the mass of that system would be changing all the time as evaporation took place, or if it was outside, if we had any type of condensation and precipitation, we could get liquid added to the system. And the container on the right has a lid, so matter cannot enter or leave the system. So we know that this is closed and this is open. So in a chemistry experiment, the law of conservation of mass is easy to observe when the system is closed. Okay? So if we look at this little diagram right here, we have a closed system of kind of before and after. And we can see we have 2 reactants here. We have element X and element Y. And when they react with each other, they form a new compound. Okay? And hopefully you can see that on the left-hand side, the total starting mass is 32 plus 2 is 34 grams. And then on the right, when these chemically react and form a new compound, the mass is 34 grams. So we see that there's no apparent loss of mass because the system is closed and there's a lid on the containers. Now, if we count the number of atoms that we start with of element X, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. We have 16 atoms of element X on the left. Then when element X chemically reacts with element Y to form this new compound, we have 2, because they're the little white or grayish atoms, 2 per red molecule here. So 2, 4, 6, 8, 10, 12, 14, 16. So we have 16 exiting the reaction in the product. With element Y, we have 1, 2, 3, 4, 5, 6, 7, 8 atoms that are on the reactant side. And when they react with element X, we get the compound, and the compound has 1, 2, 3, 4, 5, 6, 7, 8, just counting the red circles, okay, of Y. So this clearly shows that in a closed system, what we weigh at the start or what we mass out at the start should be equal to what we mass out at the end. However, it is a lot more difficult to observe the law of conservation of mass if our system is open. And this diagram is kind of helpful. I wish the illustrator had done a little bit better job counting their atoms, but let me help you see what they're trying to show here. So what we start with our reactants, and keep in mind there's no lid. Notice up here there were lids. Now there's no lids, and so it's an open system. So we have 2 grams and 32 make 34 grams to start. But then in the end, we have 31. So it appears that this chemical reaction disobeys the law of conservation of mass. But really, what the issue is one of the products is probably a gas. And because the lid is off, that gas escapes, and it looks like our starting and ending masses are not equal. And the only reason for that is because of our open system and the loss of a gas. So we have the number of atoms of X that we're starting with. And again, this is 18, I believe. 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, we're starting with 16. And what we're ending with, and we're not going to count this one right here, we're just going to count what's in the white box. So 2, 4, 6, 8, 10, 12, 14. So again, it's showing us that we have a loss of mass there. And then why we start with 1, 2, 3, 4, 5, 6, 7, 8. And we're just going to count what's in this white box. 1, 2, 3, 4, 5, 6, 7. So again, there's apparent loss of atoms. And really, the only issue is that our system is open and a gas is escaping. So think about your respiratory system in terms of being an open or a closed system. Remember, it's going to include things like your nose, your mouth, your trachea, which is just the tube that goes down your throat and leads from your mouth to your lungs, etc. The organs used in breathing. Is our respiratory system an open or a closed system? So hopefully, after thinking about this for a second, you realize that it's an open system. And the reason that we know this is because matter is able to enter and leave the system through our mouth and nose. So you have oxygen gas and carbon dioxide gas. And both of those are made up of molecules that have mass, okay, enter and leave the system, okay? Because we're constantly inhaling and exhaling through our nose and through our mouth, and we're exchanging materials with the environment, our respiratory system would be considered to be an open system. So let's do a couple practice problems here to get you ready for your homework that you're going to have tomorrow. Okay, so this diagram below shows the reaction between marble chips, and marble, the chemical name is calcium carbonate. It's right here. Here's the chemical formula, and an acid, specifically hydrochloric acid. And when these two react, calcium chloride, carbon dioxide, and water are formed. And then here's a picture of the reaction with the marble chips reacting in the acid with a cotton stopper at the top. So the reactants in this reaction, remember, is everything on the left. So we're going to put word form here: calcium carbonate plus hydrochloric acid. So those are our two reactants, okay? They're what's on the left-hand side of the equation. And then our products, remember, is what comes out. So everything that goes in must come out. We have calcium, carbon, oxygen, and hydrogen and chlorine going in. We have calcium, carbon, oxygen, hydrogen, and chlorine coming out, but what's attached to what is rearranged. So the products then are these things on the right. So we have calcium chloride plus carbon dioxide plus water. Okay, so those are our products. And if you really get a good look at this reaction, it's even balanced. So we have one atom of calcium, because there's no number next to the Ca, going in, and one atom coming out. We have one atom of carbon going in, because there's no number next to the C, and one atom of carbon going out. We have 3 atoms of oxygen going in, and we have 2 atoms of oxygen here plus 1 more here makes 3 atoms of oxygen coming out. We have 2 hydrogens going in, H2, 2 coming out. 2 chlorine going in and 2 chlorine coming out. So this is a balanced chemical reaction. So what this means is calcium carbonate will react with 2 molecules of hydrochloric acid to form 1 molecule of calcium chloride, 1 molecule of carbon dioxide, and 1 molecule of water. So, given what we know about carbon dioxide, we know that it is a gas, okay? And we know this and we can tell because look at what these little things are that are forming inside this acid, okay? These are bubbles. And whenever we have bubbles, that indicates that a gas is being formed. So, because this system is closed, we know that that gas is going to be trapped. So, is it an open or closed system? Closed. Again, we know that because we've got the cotton here to kind of block the escape of any material to the surrounding air. So, what would you expect the balance to read? Well, because it's a closed system and the gas is going to be trapped, the starting and the ending mass should be the same. So, I would put 180 grams. How do you know? It is a closed system, so gas will be trapped. Okay? If you heat a piece of copper, okay, the copper combines with oxygen in the air to form a black layer of film called copper oxide. So this is a completely new scenario. So we have a piece of copper and we're heating it up with a flame, and it's going to combine with oxygen from the air. So already you should be thinking that this is an open system. If we think about just the copper as the system, it's an open system because it's reacting with oxygen out of the air to form a black film called copper oxide. So if we write the word equation for this, we're going to put copper plus oxygen equals copper oxide. Okay, we're going to write it in word form. And again, the copper is the system, and we know that it's an open system because oxygen from the air, from the surroundings, are going to react with that wire or the copper in the wire. So how would the mass of the copper change over time as it was heated? Well, keep in mind, this oxygen is coming from the air and it's reacting with the copper atoms in a copper wire, and you're getting a new compound that has copper oxide. So what I would expect to happen, as odd as this sounds, is I would expect the system or the mass of the copper to increase. Okay, I would expect the system to gain mass. And the reason why is because oxygen from the air is chemically combining with copper to make a new substance, and the mass of the oxygen atoms are added to the copper. Okay, and again, that oxygen is coming out of the air and reacting with the copper, and so it's actually adding mass to the system. So what I'm going to have you do is fill in these notes, and then tomorrow you'll be doing a homework assignment related to conservation of mass and open and closed systems, and really trying to apply these concepts. Now, if you have trouble with the assignment, you should look back at these notes and hopefully they will be helpful to you.